Welcome, everyone, to the 137th meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Simone Virili from the Autonomous University of Barcelona, and he'll be talking to us about locally finitely presented Grothendieck categories with a flat generator.
So thank you for the invitation and for your interest in this research. Let me try to share the screen. Let me see. Can you see something now?
Yeah.
Yeah. Okay. So you see the full tablet. Okay. So as we said, the title is locally finitely presented Grothendieck categories with the flat generator or with enough flat objects. I don't remember exactly. This is a joint paper with Lorenzo Martini, Carlos Parra, and Manuel Saorín. Even if it started in a kind of a strange way because it was a process of a lot of years. A few years ago, I started to work with Manolo on some problem, Manolo and Carlos on some problem. Then they started working with Lorenzo on some other problem. And at some point we realized that it was the same problem, but that was just already part of the solution. So let me start introducing the two problems, and then we will see if we can see that they are equivalent. So as I said, we will be working in locally finitely presented, and Grothendieck categories. And so Grothendieck category, you already know probably that this is just AB5 abelian categories such that they have a generator. So, and direct limits are exact and so. And once we have this, we can define what being locally finitely presented means, and this just means for a category, say, Grothendieck category, say, G, to be locally finitely presented just means that every object is a direct limit of the finitely presented objects, where an object X is finitely presented. Is finitely presented. If and only if the functor represented by him commutes with colimits. Directed, sorry. Okay. Okay, so this is the categories we will be working with. In these categories, there is a very well established already purity theory that allows us to define flatness. Nevertheless, we will be working with localizations that we don't know a priori if they are locally finitely presented. So let me just give you a notion of flatness that works for any Grothendieck category, and so we know what we are talking about. So if we start with G, that now is just a Grothendieck category, we say that a short exact sequence, say 0 to x, y, z, short exact sequence in G is pure if and only if it is a direct limit of split sequences, split exact sequences. This notion does not need anything, and it behaves pretty well. It gives an exact structure, and yeah, you can do almost all the things that you do by hand with the other purity. You cannot really do model theory, but still it behaves well for what we have to do. And once we have this notion of pure exact sequence, well, we can say that an object f in G will be flat if and only if whenever we have an epimorphism onto F, this is always poor. Okay, so this is just to be sure that I will not say flatness in a category where it was not defined. But yeah, whenever we have some important result, it will always be for locally finitely presented categories where this notion of flatness coincides with the usual one. Okay, so this is the object we are working with. Yeah, sorry, just one other definition before starting. I will be needing to know what an AB4 star Grothendieck category is. And this it just means that the functor products are exact. Okay, so with this little dictionary, we can start introducing the two problems I announced. So the first one is due to Cuadra and Simson, and the year 2007. And it is about flatness. So, well, the first part of the problem is a bit generic, a bit imprecise, but it is just characterized the locally finitely presented Grothendieck categories with a flat generator. And I state this even if it is a bit imprecise, because in a way we will also be doing part of this, not really a characterization, but we will be giving a new characterization. No, not really structure theory for those, but at least a criterion. And the second part is a problem that was already solved by Rump, that was to try to extend the flat cover conjecture to those Grothendieck categories that had enough flats, but as it was already solved, I'm not writing it. And the last part, so let me say 2 here, is so suppose that our G is locally finitely presented, and there's enough flats or flat generators. Then, does this imply that it has enough projectives? Okay, so this is the first problem. The second problem is more a question than a problem, actually, but okay. By Aurélien Germain. He actually posted this on Math Overflow, and then he wrote me because I had some related papers, and for many years I was not able to do it, but then, yeah, then Manolo and the others had some good ideas, and now we know how to look at these things. So the question is, it starts exactly the same. Start with G, which is a locally finitely presented Grothendieck. And he also allows other cases, maybe locally coherent, which is precisely the same as locally finite. Yeah.
Can I ask a very stupid question? What
Yeah.
is the usual definition of flatness in locally finitely presented Grothendieck categories?
You can do it, for example, passing to the category of functors. Okay, and then there would be exactly, no, the Yoneda embed, the restricted Yoneda embedding is not exact. And so those exact sequences that remain exact when we embed them in the, but you can see that it is exactly the same as direct limits of split exact sequences, because they are exactly the unit things that are preserved by Yoneda. And whenever you are in a category of modules, even over a small pre-additive category and so on, then there is a notion of tensor product that you can use. But it is not the same as the geometric tensor product. No, that is different.
Okay.
Okay. So locally coherent, that is just the same as locally finitely presented, but where the category of locally finite finitely presented objects is actually abelian, and maybe even locally Noetherian. Okay, which is abelian but close on the sub-objects in the bigger category. But yeah, the most interesting case is still the one of locally finitely presented. So in this case, he asks, suppose that G is A before star, then the question is the same. Does it have enough projectives? And okay, so these are the two problems, and let me start telling you how one can try to construct some counterexamples, no? Because these are pretty general questions about Grothendieck categories, and it seems that you will never be able to find a counterexample if you stay too close to categories of modules, no? Because categories of modules are precisely the ones that are well, generated by projectives, always have enough flats, and always have exact products. So we have to start to build new categories that are not just of modules, and the usual way to do it is with localization of Grothendieck categories. So we start now with our G. Now, for the moment, it can be just a Grothendieck category. And let us fix inside G a subcategory T, which is what is sometimes called localizing, or sometimes a hereditary torsion class, which means that it is closed under subobjects, quotient objects, extensions, and arbitrary direct sums. Whenever we have one of these categories, we can build a localization sequence. So the embedding inside G, this has a torsion adjoint, and this goes to the quotient category that has an adjoint which is fully faithful. And the important thing here, this is exact. Okay, this is the standard way to localize things, to build new Grothendieck categories that are farther and farther away from module categories. But with just this construction, there is not a lot of control. There are some criteria, but even if I know that G has very nice properties, it is A before star, it has flats, it is locally finitely presented, usually it's very difficult to ensure that the localized category has any of these same properties, and sometimes they appear just not coming from G. So it is, I mean, it is very well behaved for some things, but not exactly for this kind of problems. But there is one particular case that is when T is closed under products. So it is what it is usually called a TTF, because it is at the same time a torsion and a torsion-free class. Then we have also left adjoints to the functors above. No, so let me redraw it. So we have this, and now we can consider these other adjoint functors. And especially this functor here, is what makes everything possible for us, because whenever, say, let me call this in the usual way of Recolman, so this would be, say, J star, and this J lower star, and let me call this J lower shriek. Then say J lower star of the localization viewed as a subcategory of G is what is usually called sorry sorry, I forgot the name. Okay. Okay, but the important thing, instead of considering this subcategory, which is of course equivalent to the quotient, we will consider the other embedding of the same category inside G. So we will consider zero subcategory. Sorry, we will consider this other embedding inside G. This is still equivalent to the quotient category because this is a fully faithful joint, but we will consider this inside G. So let me call this, let me give it a name. It should be XT for the moment. We will see it inside the category G. And the importance of this is that it will give us very trivial criteria to study the class of finitely presented of flat objects inside the quotient category. And so, yeah, but okay, there is a problem in general that TTF classes are not enough. There are very few of them. So, in fact, let me just parameterize them. No? There is this classical theorem by Jans, by this an old theorem from 1965 that tells that, well, for any ring R, there is a bijection between idempotent two-sided ideals of the ring, so inside R, and TTFs. Classes in, say, mod R. So really this, the recalment that I drew before, if we start in the middle with the category of modules, they are all of the following form. No? So the TTF class just corresponds to the category of modules over the quotient ring. And here we have the prototype of all the examples we will construct. This is this localization over this TTF. And here we have our embedding. Here it is the usual zero embedding. And yeah, the important class for us will be for any ideal of this kind, the image of the localized category inside R that now we will call Xi, no? Because like the parameterization of these TTFs. Okay, so let me just give you already the criterion that I announced. So we stay in the same setting. That is, R is a ring, and I is a two-sided idempotent ideal of the ring. Then, in this generality, without any hypothesis on the ring, we can say that the finitely presented in this category Xi, remember that Xi is equivalent to the category GI, which is the one that interests us. So if we are studying finitely presented objects in Xi, it is equivalent to studying that. But now, as this is embedded in a very nice way in the category of modules, these are exactly the intersection of Xi with the finitely presented modules inside R. The same holds for the projective objects. So the projective objects in the localization can be seen as the intersection of this class Xi with the big class of projectives over R. The same holds for the flats. And okay, there is one more thing, and we can also recognize the generators. So first, I'll say if we have a set X, a family of objects inside this Xi, this generates Xi if and only if I is the trace of S in R. So this is a very algebraic criterion to transform this categorical property. Of all the things that we have mentioned for these two problems, there is just one that I haven't mentioned, that is the A before star property, but it is just because any such GI is A before star, and that is not that very surprising because we start with a category of modules, which is A before star, and we localize with respect to something that is close with respect to products, okay? And, but also, a consequence of this description of the flats allows us to say that it always has enough flats and of course can just specify the condition for and it has enough projectives if and only if the ideal the ideal I is the trace of a projective. Projective right harmonic. I specify writer module here, and even if I'm mostly of them, I'm not that careful with that, just because we will have two criteria: one for local finite presentability of the quotients, and the other for having enough projective. And one will work with left properties of the ideal, and the other with right properties of the ideal. But yeah, okay. So you see that if we manage to find a ring R with a two-sided ideal, an important ideal, which is not the trace of a projective, and we manage also to show somehow that this quotient category is locally finitely presented, then we will have found a counterexample to both problems. So this is the original idea, say. But of course, one may expect that this is just a little sample of possible examples, but that most of them can escape this form. No, but in fact there is an old theorem. I don't remember. Yeah, okay. I don't know if I wrote it wrong, but here in my notes it says that it is the same year of Jan's theorem. That it is a theorem of Roos. That classify that say it is a representation theorem for A before star plus AB6 Grothendieck categories. And essentially it says they are all of the kind like a localization of a category of modules over an idempotent ideal. But just let me tell you what AB6 mean, and then I will give you the theorem. So AB6 means, well, there are several ways to say this, but probably the simplest is, say, for any I will tell you this in general. So G a Grothendieck category that you can think category of modules, whatever. So AB6 is, so for any X in G, we take a subobject of X and we say that it is of finite type if and only if for any direct system of terms, direct system, say xi, I in I, inside the lattice of subobjects of X, so it is a monodirect system, such that X is the direct union of these xi's. We have that there exists some I in I such that F is contained in that specific xi. So this is essentially a compactness in that lattice, or more generally, if you want, whenever you have a finitely generated object or a finitely presented object in your category, which is a sub-object of something else, then it is always of finite type. It's just a generalization that works even if you are not in a category of which is locally finitely presented. But this observation tells us that local finite presentability always implies AB6. So, okay. So with this, knowing now what this means, the theorem by rules tells us that if G is, what I said, AB6 plus AB4 star Grothendieck category, then there exists a ring R with a two-sided idea which is idempotent I, such that G is equivalent to GI. So this is still not the end of the story for the Cuadra and Simson problem, but at least for the Jamin problem, yeah, it says that all the examples, the counterexamples we may be able to find are of this kind here, no? Because in that case we have local finite presentability that implies AB6, and he asks explicitly about AB4 star. So the next step is to try to put also the other problem inside here, and then we can just stay over rings with an idempotent idea. And I can give you the idea, but I give you let me just give you a general statement, and then I can maybe try to give the idea of why it is true. But this, I think, it is my favorite result of this work. And this says that for any Grothendieck category G that is locally finitely presented, the following are equivalent. One, G is AB4 star, and two, G has enough flats. And this is a connection that I was not expecting at all, and but yeah, it is actually true. And okay, on one direction now you already see that it is by the theorem of rules, because now, for example, if we want to go from 1 to 2, well, we already know that the G is equivalent to G over I for some idempotent ideal in a ring, and we have already seen that all such categories have enough flats. As a consequence of that criterion of flats in the quotient. The other direction is a little bit trickier. So I will not be able to give you a proof, but at least I will try the idea. And it uses what is usually called the projective effacements of objects, because by another result of rules, our category G is A before star if and only if any object in G has a projective effacement. And this is not surprising, actually, because it is very common to prove that something is A before star just using some kind of generalized element from some family of projectives. This is the common way to do it in modules, but in functor categories and so on. But and here, these projective effacements just play the same role as the projectives, even if they are not as good as having projectives. But once you have this, this plays very well with the local finite presentability of the category, because we can start now with our object X inside G, and we want to construct a projective effacement, not to say that it is A before star. Oh, sorry. Have I written all the numbers? No. Okay. Sorry. Yeah. Okay. So we start just taking writing it in the canonical way as a direct limit of finally presented. Then we take the canonical epi yes, sorry. From so yeah. Yeah, sorry. I will go on with the rest. Let me just tell you how to fix this. Yeah, I should have done another thing before, because you first start with your object X, you cover it by some flat, and then you write this as a direct limit of finally presented, and you take this big epic here, and the composition here is what you need. Sorry, I did a little bit of a mess, but yeah, sorry. Okay. Anyway, let me just try to make the point of where we are. So now we have, okay, first of all, we know that A before star is the same as flat generator for locally finitely presented Grothendieck categories. And this tells us that the Cuadra Simson problem is equivalent to the one posed by Jamais. And so now, to try to solve them in the negative, we want to find a counterexample. We said that any possible counterexample will be of the form So any possible counterexample is of the form Gi with I an idempotent ideal in some ring R. And we have criteria for almost everything for this kind of categories. We know how to look at the floods, the products. The unique thing that we have not mentioned and that we need is a criterion to understand when these are locally finitely presented. And this is the next result. That is the last abstract ingredient for these constructions. So a theorem, I will give you two different criteria. So let's start with R ring. Our idempotent idea inside R. And then we say that if at least one of the following conditions holds, Gi is locally finitely presented. Okay, so the first one is just that the suitable restriction of the multiplication map from I times I to itself has to be an isomorphism. This is like the first half of the condition, and the second half tells us that asks that ER is finitely presented. Okay. Here, finitely presented as an object in the category mod R. Now, this is the category because now it becomes a bit subtle. So this is the category we are studying. So this I mean as an object in our category. Second criterion, I as a left-R module now is pure as a subobject of R, so as a left ideal. Okay, so sorry, all of this. And this, of course, why does this left module appear? The fact is that here we are taking I as an object in the category, and here we are making it act on the category. Because now we are in categories of modules, so purity can be described by tensor products, and to have this I act on right modules, we need to have it as a left module. No? So by this would mean exactly that the canonical map like this to M. Now M viewed like M tensor R is injective. Is monic for all M in small mod R, so finitely presented module. Okay, so now we have criteria for all the conditions that we want to verify or not to be true, like the one for like the projective generation. We need a concrete example. So we were just able to find one, and actually not us alone. We had help from Dolores Cervera. And Pavel Prihoda. And they are very expert working with projectives and traces of projectives. And so when we asked them about these kind of examples, well, they first thought they had many, then they found, but in the end, at least they found one. And in this example, it actually becomes very easy to apply all the criteria we have. And actually, in the previous page, I gave you two criteria for the quotient category to be locally finitely presented. Well, we have just one example, but it satisfies both criteria, and we have no other. So it is impossible that they are equivalent. We don't know. But okay, so so the example is what is usually called a Dubrovin Puninsky ring. And this is a class of rings that appears as endomorphism rings of a very special little module over nearly simple domains. So we start with R, a uniserial. I'm not in the commutative order here, no? So by uniserial, I mean left and right. And I suppose that it is a domain. Then we call this domain nearly simple. If, say for all A, B in R, probably excluding 0, we have that the module cyclically presented by A is equivalent, is isomorphic to the module cyclically presented by B. So there is just, there is the torsion-free module, the cyclic one, the R itself as a module, and then as torsion modules, there is just one cyclically presented one. So it is very special, and then we give it a name and we call it X. So the Dubrovin-Puninsky ring that we need is the associated Dubrovin-Puninsky ring is endomorphisms over R of this X. And okay, now we have the ring. We need the idempotent ideal, and the idempotent ideal here depends on the size. It can be either the one of non-surjections or the one of non-ejection. They both work actually, but let's take just be sure about the size. Let me check the one of non-epimorphisms. Okay, so let me take I. So all the say phi and X that we will call S from now on, such that phi is not AP. And this is actually just one of three two-sided ideals that this ring has. So we have the non-epimorphisms, we have the non-monomorphisms, and then we have the intersection, which is the Jacobson radical. There is nothing more. And this duality between non-epimorphisms and non-monomorphisms is actually very nice because every property, purity being the trace of something, all the properties we will work with, if they work on the left for the ideal of non-monomorphisms, then they work on the right for the one of non-epimorphisms and so on. So there is a very nice duality dealing with elements that one can play. Okay, this is the ingredients. So proposition. What properties do they satisfy? So in this notation, in the above notation, we have that. Well, first of all, I is idempotent and the two-sided ideal. Then we have that as a left module over S, it is finitely presented, which was half of one of the criteria that we had. It also satisfies the other half, that was that the tensor, the product, restricted product map from two copies of itself to itself is an isomorphism. And it also this would be enough actually for this, but okay, it satisfies also the other criterion, and as we don't have other examples, let me just tell. So this is pure as right as module. And finally, which is the difficult part and the unique requirement that we are not able to find in other classes of examples, I is not the trace of a projective model. Okay, so let me just conclude this now with why this is nice. So the associated localization GI will be a locally finitely presented Grothendieck category, which is AB4 star, that generator, but not enough injectives. And this is what follows, strictly speaking, by the criteria, but then in the particular case, we can study it a little bit deeper. And then in this specific case, we can even say that actually there is no non-zero projective object in this category. And furthermore, as the ring R with star, sorry, the ring S here, this endomorphism ring, is locally coherent, and we are localizing with respect to something which is of finite type, then this remains locally coherent. So it is not just an example of the German questions for locally finitely presented, but it also solves the case of locally coherent Grothendieck categories. So the unique case of that question that still remains open is the locally Noetherian case. Not the same question, but locally Noetherian categories. Okay. I think it's complicated to try to explain you why it works. But
Sorry?
Also...
you wrote enough injectives there, so the typo should it say enough projectives?
Oh, sorry. Yes, thank you. Yeah. Thank you. So I was just saying that the proof is actually not difficult to read, and it is based essentially on the fact that all the elements of our ideal are actually acting on this initial ring, on this object X, but this object X is a quotient of this uniserial thing. And so something to be the trace of a projective, you have to be the content of a big matrix, big idempotent matrix of coefficients in the ring. But such matrices will be row finite, and you just try to describe the images of those coefficients inside this thing here, and as it acts on something that is uniserial, you see that all these images have to be nested, and as this row finite, then you need to have a maximum at some point, and this forces a contradiction. But it is a very nice argument due to Pavel Trifoda. And okay, so this proves that both problems have a negative solution in general, but the fact that it was so difficult to find a single example and that just we have one, it probably suggests that in many cases, one can give also positive results. No? So by positive result, I just mean, well, instead of working with any Grothendieck category, we restrict to some specific class of Grothendieck category, we study a problem there. And yeah, in fact, in many cases, there are, having enough projectives is equivalent to having enough flats, which is equivalent to having exact products in a lot of cases. So let me just give you some example of this kind of hypothesis we can add. So the first one is very natural, but kind of different from all the others. So I will just do this fast. And it is, if R is commutative, then for all idempotent idea in R, we have that the following are equivalent. So are equivalent for GI. So A before star, flat generator, and enough projectives. Okay, the following are kind of more interesting for me, because here the proof is no, okay. I mean, it is on the archive if you want. It's just a little play with commutative localization. But one that is even easier but has much stronger consequences is the case when R is a von Neumann regular ring. And as I said, in this case is trivial. The problem because one can characterize the von Neumann regular rings, for example, saying that mod R is equal to proj R, so the finitely generated projectives and the finitely presented are the same, but also that mod R is the same as flat R, and of course products are of course successful because we are in a category of modules, and also you cannot actually localize these categories because yeah, it is essentially just taking quotients and little more. But there is a slight generalization that actually has big consequences, and it is when R is semi-regular. And this just means that R over its Jacobson radical is von Neumann regular, plus the condition that idempotents lift modulo the Jacobson radical. And then, yeah, here, even if this von Neumann regular case is really trivial, well, this second case here, even if it is essentially easy to prove because you have a lot of splitting in here and you can lift all the splittings, but this actually has, I mean, this example, for example, if you take any decomposable injective, its endomorphism ring will be semi-regular. So these are rings that happen a lot. And for example, one of the consequences is this. So if G is now locally length Grothendieck category. Sometimes they are called locally finite Grothendieck categories, but what I mean it is a locally Noetherian Grothendieck category, such that every finitely generated object is also Artinian. So you have a composition length on all the finitely presented. And so. Okay, so we have this kind of category, and okay, for these categories also we have a positive answer. No? So for these categories we have that having enough flats is the same that being A before star, which is the same of having enough projectives. And in this particular case, we can add one thing, and it is also the same as having enough, say, let me just put it in quotes, enough finitely generated projectives. That is a fancy way to say that it is a category of modules. So any of these properties is equivalent to this Grothendieck category to be already a category of modules to start with. And why do I say that this is an important case? Well, because a kind of categories that is a locally linked category is the original motivation for this problem by Cuadra and Simson. And this is the following corollary. So let's fix a field. Okay, is a field. Say take C a K coalgebra and consider the category G, the category of C comodules. Then this is a local length. Length Grothendieck. So they had actually asked the question to solve this specific example. They wanted to know if for this kind of categories, having enough flats is the same as having enough projectives, and the answer now is then, so yes, for these categories it's true, but it is not true in general. And I know that I'm probably a little late now, but maybe we start maybe 2 minutes late. I just wanted to give one final connection with another problem, because also that is very surprising, at least to me. And it is a connection with the telescope conjecture and triangulated categories. And by telescope conjecture, I mean actually the non-stable version. So for T structures and not just for localizing categories, non-stable. So very fast. Let's start with the compactly generated triangulated category. And if you want definability to be easier, we can assume that we have at least some kind of model that tells us what homotopical limits are, but otherwise, well, yeah, let's assume that tacitly, and let's take T to be a this structure on D such that the coil is definable as a subclass of this triangulated category. So it's definable, which means that it is a coil, and plus that we have to add that Y is closed. Y closed under directed homotopy limits and pure subobjects in the sense of the purity theory of in compactly generated triangulated categories. Also, the second requirement of pure subobjects is if you have good enough model, probably it's not necessary, but to be sure. Okay, whenever we are in this situation, Krause introduced an ideal IT with respect to this structure. Well, he did it first for localizing classes, but it works the same. It is an ideal, not really ideal of a ring, but ideal of a pre-additive category, which is the category of compact objects, and it is the ideal of all the maps from between two compacts. So a map in the category of compacts, such that this map is sent to 0 by the co-representable functor associated to any Y in the coil. So, and okay, he also proves one other thing, and that it is that this, at least for the structure whose coil is definable, it is always true that this is an idempotent ideal. So we can try to take as a category of modules the abelianization of these categories of additive functors to abelian groups from the compact objects, and take the corresponding quotient with respect to this two-sided ideal. It is just working with rings with enough idempotence, no? So the theory will work perfectly also in this case, and we try to see what happens. And this is the result. So in the above setting, so let's define, say, mod R, sorry, mod DC. It will be the category of additive functors from DC up to abelian groups. So additive functors. And inside this category, we take this T, I, T, it will be this category here. No? This is our torsion class. And then we can take our localization, GIT, to be precisely this mod over this T. Sorry, IT. Okay, so the following are equivalent. One, well, we have two words, not the triangulated and the mono one. So one is that this abelian word has enough. Sorry, it is locally finally present. So not locally finally present. Which corresponds to T is compactly generated. generated. These are equivalent. And the way to pass from one to the other is that, well, the second thing here is also equivalent to a more algebraic condition, which is that this ideal here is generated by identity morphisms, identities. Yes. Which seems strange if you are not used to working with rings with enough idempotence, but essentially it's telling you that this is the trace of finitely generated projectives. So also in this case, we will have a positive answer for this kind of things because, well, we will have that locally finitely presented is the same as enough small projectives, and but now it characterizes also the compact generator of a definable T structure. Okay, sorry for the delay. That's all what I wanted to say.
Thank you, Simone. Let's give the speaker the floor. If you have any questions, please ask them now. The equivalence within number 2 here on your screen, that's due to Henning, right?
The equivalence between what? Sorry, between
No, the
two
inside number 2, the equivalence that
yeah. That is, I think it. I mean,
that's due to Henning, right?
at least for the case of stable torsion T structures for localizing classes, it is for sure of the original paper where it was introduced by Henning. Then I don't know who did it for T structures, but yeah, it is not ours to result. Maybe just two comments, practical ones. First, the paper is all written for rings with enough idempotence, so actually for pre-additive categories, because yeah, we need to be able to handle also this kind of examples. And also, if you are curious and you want to go see it on the archive, I suggest you just wait 3-4 days because we are just updating the new version and it is much more readable than the previous one. So.
Thank you. Any other comments? I had another small comment to well, this GIT, this growth subcategory. How, I mean, in practical examples, is it at all easy to check if it is locally finitely presented?
No, I don't think so. But at least I mean, it is impractical to look at it, and that's why these kind of algebraic criteria are kind of nice because they are localized inside this ideal. No, but I don't think it will be much easier than just working with the ideal I that Henning had. But it was just nice for us that this criteria that we developed in completely different setting could be used also not just to describe some cases, but they are actually equivalent to this structure being compactly generated. No? It was surprising. No, but yeah, of course, all these criteria are aimed to take some property of the quotient you don't understand and transform it in an algebraic property of the ideal. But if you already have the ideal, like here, I don't think it gives you a lot of new information.
And do you know if there's any hope of, for example, again, like staying on this theorem, generalizing from compactly generated to well generated, where instead of the T structures being, I don't know, LF0 compactly generated, you would just have a regular cardinal.
I mean, it's the usual thing with the lack of enhancements, no? That yeah, compact things work well, and
Yeah.
probably the rest will also work well, but you have to have enough interreality, no? And so probably with infinity categories, I'm sure you will be able to do something like that.
Okay. Thank you.
No, because I mean the theory of the set theory of definable is perfectly inside. It is independent of the ordinal. But yeah, here.
Right. The set theoretic part is independent of the ordinal arithmetic.
No,
Right?
but there are theory. I mean, there are differences. Not the countable case is always
Yeah.
usual. Always easier, but yeah, this. Mm, yeah, I mean, all this theory of purity is all done for all ordinals. You know, it's not done just for the countable ones.
Yeah. All right. Stop asking questions myself. Does anybody else have any questions for Simone? Well, if we don't have any questions, let's thank Simone once again.